first, let's talk about the past, and then we'll talk about what's coming next. So I always look back at 2011 as a pretty important year in my technology life and my company's life. This is really when Silicon Labs went all in on IoT. And at this point, that means smart, connected, secure, intelligent. But back then, we didn't know what it meant. And I remember Ericsson published this famous landmark report that said there's going to be 50 billion things out there. And of course, they thought they were all going to have a cellular connection because it's Ericsson. Well, they weren't far off. And another thing happened that year. Apple unveiled the first phone with native support for Bluetooth Low Energy. So this was the first time we were talking about a data link to the real world that was really IoT-centric. Prior to that, there had been IoT networks and there had been IoT use cases, but this is the first time we had a premier consumer-facing company saying, it's not all just going to be content, we're not just going to be streaming things, we're also going to be interfacing with the real world, and our phones need to be one of those hubs. So their phones wanted to see into the real world and do things with it. Today, or near today, we are not far away from 50 billion units. This number is I think, little dated now. I think we're probably over 50 billion installed devices for IoT that are connected. And they're kind of taken that prediction a long time ago, and it's pretty darn close. And for a long time, I got started in the IoT business back in 2012, and nobody believed it. Nobody believed it. I mean, smartphones weren't even really standard in most of the world. And they're like, how are we going to put all this wireless technology into the world? And then once it's there, what the heck are we going to do with it? So now we have all this potential. I like this example of a cat with an AirTag, because if you talk to a developer 10 years before and said, we'll have a low-cost way for you to find your pet, so low cost, you're tethering into an existing ecosystem running on data networks that were built for somebody else, into an operating system that the world hadn't really globbed onto yet, they would have thought that was pretty crazy. So now we can do pretty much whatever we want, including a bunch of AI stuff. Oh no. There's some text missing on the slide. But I like to say embedded's the biggest computing platform in the market. You know, this data here, there's really about 15 billion embedded devices that ship per year, billion with a B. It dwarfs all the other markets combined. Data center, PC, mobile, automotive. Really, embedded is where most of the computing in the world actually happens. This is by count where the things are. And there are thousands of customers. In the other markets, there's really 10 or less that matter, and we sell to thousands. Silicon Labs has over 5,000 customers just in wireless, more on the MCU side. And we have other constraints. This is where edge AI starts to really get felt. We have constraints in power, and bandwidth, and cost, in lifetime. Our stuff has to last longer in many cases. We don't replace a water meter as fast as we do our smartphones. And it's going online now. Data centers really got connected in the 80s, PCs with the early dial-up modems in the 90s, and then phones came at the next wave. Embedded is getting connected now. And once it's connected to the cloud, it becomes very rich for AI use cases. I like to say most AI things in the world will have wireless, and they will be connected to the cloud. It's very rare that you're going to have air-gapped AI. It will be there, but it'll be rare. So that's what we do. We break that air gap. We connect stuff to the cloud. That's Silicon Labs. That's kind of what I've dedicated my career to at this point. I love it, and I love this technology, and I love bringing really cool products to the market. And you're going to see a bunch of product stuff in this presentation here. So we're going to go look at a few eras here, going back to 2007, and then we're going to project some things going forward from there. Because AI at the edge is really the last step in a sequence of events that's been unfolding for almost 20 years now. And I first put a slide like this together back in 2017 because my boss at the time said, what the hell is next, Daniel? You know, we've had these MCUs and we're putting radios next to them or inside of them. Where is this all going to go? Please tell me we're not done. And I said, well, that's a great question. We're definitely not done. And so I kind of broke these things down into eras, and I said, look, the next 5 years, we're going to be really contending with absorbing the wireless impact and the compute that is continuing and securing these devices. And the 5 years after that is really going to be about AI, making things truly smart. So what happened in the first era back in 2007, or around 2007? I think that's really important because prior to this time, most of the instruction sets in the world were proprietary. We all take ARM or RISC-V now for granted, but prior to this, it was a fight. It was MSPs versus AVRs versus PICs versus Power PCs versus, you pick it. Custom tool chains, assembly in a lot of cases. And then ARM came along and said, look, we're going to create this Cortex-M portfolio. They started licensing it in 2005. It got launched in 2007, and now it's taken most of the customer-facing side of the market. RISC-V is more recent, and it's there, but it's more captive cores, not yet customer-facing cores. And so here's just a data point showing how fast ARM's processors took off. There's a survey from 2019 showing what processor architecture are you going to use. It's basically all ARM now, or it was back then. And they really took the market. So we standardized the instruction sets. And that was good. That's good for the market. That's good for the customers. The silicon providers fought it until they all went with it. So here are some products along the way. And the formatting got a little messed up when they were copying these in. But here's some products along the way that kind of show the progression. The first kind of pinnacle, one of my favorite products of all time, is the STM32F1. That was really what made this go. Without that F1 part, I don't know, well, somebody would have done something like it eventually, but it's really innovative for ST to go off and do that. Very simple product, and things have evolved since then. MCU technology really gets the benefit of Moore's Law and will continue to do so for a long period of time. So you can see clock speeds running up, memory running up, power consumption moving down. Power consumption moving down. There's a theme here. And again, we are moving along Moore's Law. Started at 180. The MCUs in the market today are typically, non-automotive MCUs are typically in 22 nanometers and above. We'll all hit FinFET in the next 5 years. The next big thing that happened was standardization on connectivity. So I talk about that iPhone moment. This was very important. Prior to kind of this era, most of the wireless in the world was proprietary. Proprietary or very niche. Both of those two things, sometimes niche and proprietary. I like the iPhone moment because it really set the world to the idea that we're going to have a lot of low power, short range wireless connections. And Bluetooth is going to be one of them. Prior to this, Bluetooth was really, remember the headsets? Or you'd use Bluetooth to replace your printer cable. It wasn't as big as it is today. And the plot here you can see is a kind of non-cellular based Bluetooth growing very quickly. So from 2011, where almost you had none, to around now, it's on par or bigger than the number of Bluetooth chips that are shipping in cellular phones together. So we're talking about billions of Bluetooth devices shipping per year. 10 years before, there really weren't that many. There really weren't that many. This is specifically BLE, not Bluetooth Classic. So Bluetooth took the market, and it also paved the way for more standardization in wireless. And that's a good thing, just like it was a good thing in processors. Standards help the ecosystems. Standards grow the market. They focus our R&D, our collective R&D, in the right places. Every company wants to have everything, honestly, but there's a lot of duplication and waste. I think it's just better for everybody, the market, humans, citizens, if we're dividing and conquering. So here are some examples of products along the way. The Nordic NRF51 was kind of a pinnacle, pioneer, leading way of this that got launched in 2012. I remember that. I was living in Norway at the time, and we were doing low-power MCUs, and we're looking at this thing like, how big is this going to get? And now Nordic today is kind of built on that. It was a little bit more than the MCUs you saw in the STM32F1. It took some more power to kind of run these protocol stacks. A lot of MCU customers were like saying, hey, the wireless portion of this is actually bigger than my application. And we're going to see the same thing happening in AI, by the way. Their application may be one size, and we may be asking them to take on a whole bunch of cost and complexity that is far bigger than the core application itself. So wireless has really advanced. We see better processors, evolution of the standards here. So the wireless standards are evolving much faster than the processor standards. The instruction sets kind of get set once, and they very rarely refresh. But in wireless, it's moving real fast. And in AI, it's moving even faster. And again, Moore's Law, 180 to 90 to 40. And now we're launching our wireless SoCs in 22 nanometer. That's kind of where everybody is at in the market today. These products are also starting to get very feature-rich. Once you have a wireless link to the cloud, I like to say the cloud, it's not just data moving up, the cloud kind of comes down. And it changes the way the application is built. It changes the expectations on that end product from what you can sense, software that you have to update and patch, and a whole bunch of other stuff. So the silicon needs actually get bigger once you connect an end product to the cloud, not the other way around. Next is security. So once you have all these MCUs that are connected to the internet running around, it's just a big gaping security hole, right? And locked, unlocked, debug ports, attacks from the cloud, we're all gonna, airplanes falling out of the sky. I don't really know. But that was the next big thing. And we spent the last 5 years really trying to secure these applications from both remote and local attacks. This is just some news about things that have happened, door locks, cars that can get hacked, remote attacks on medical devices. Nobody wants this stuff. It's actually not that hard to throw up a huge security barrier because we're just like in the past, we're adopting technology from other markets. Embedded gets to adopt security technology from markets like mobile and PC and at a very low cost point. So it doesn't break the bank for my customers. So here are, again, some products in the market kind of from 2015 to 2020. Kinetis K81 is one that I've always liked. That was a kind of innovative part from Freescale. And they have a big security business inside. And they're like, let's start bringing that security inside of MCUs. Let's not just have the secure element sitting outside. And that's what they did. But there was no wireless on this chip. So it's an M4, 150 megahertz, no wireless yet. I think they were building them for point of sale terminals, is what I think it was for. So you can see basic security functions coming in. True random number generators, not pseudo-random anymore. Tamper detection, elliptic curve cryptography with hardware acceleration on this. So versus running it in software, you can do it for much more securely and much more low power with these accelerators. We're doing the same thing in machine learning now, and we'll talk about that in a minute. Kind of the targeting of the processor versus targeting of accelerators is a really big determining factor for my customers' use cases. We're seeing the same progression over time. Cypress with their PSOC 6, Cypress now Infineon, was a big step forward. It was really the first big security thing with Bluetooth. We launched, Silicon Labs, a ARM PSA Level 3, the first ARM PSA Level 3 certified chip in 2020. And there's a heck of a lot of security features that come in with that. We're very proud of that because we wanted to kind of enable the customers to do it the right way. And I truly believe in a world where privacy is something we should have. And I wanted it for the IoT, not just for computers and phones. And that brings us to now. So in each one of these, there was a kind of catalyst moment. ARM PSA in 2017, Apple iPhone in 2011, ARM doing the M3 in 2007. And looking back, it's kind of easy to identify what those catalysts are. I don't know what the catalyst is now. Maybe it's already happened, and we don't know what it is. Maybe it was ChatGPT. I don't know. Kind of capturing the public consciousness and making them aware that you can do a heck of a lot with this stuff. In the past, and up till now, arguably, we have limited processing in these end nodes. We send all the data off the device. We flood the network with garbage data. It's terrible for the spectrum. It's terrible for our customers because now they're storing all this data in the cloud. They're liable for it. They don't really want it. Most data is not that interesting. They would rather just get the actions, the insights, the intelligence from that. So they're doing very cool things with it. These are three kind of staple examples in maintenance of equipment in the field. They want to build products that are maintainable with AI, not just built to last forever. Those are very different business models. They want to do things like make things more performant, higher quality. We have security customers that are embedding AI technology into sensors to reduce false positives. I mean, your business model as a security vendor lives and dies on false positives. And your relationship with emergency services is made or broken because of false positives. And so anything you can do to remove the false positives, because their systems are biased towards that. You'd rather have a false positive than a false negative. That means someone broke into your house and the system didn't go off. So they're always tilting towards false positives. We're also seeing a lot of AI technology coming into consumers' hands, through medical. So there's a tremendous amount of technology being invested, not just by the big companies, the ones you think about as tech companies, but even traditional medical companies. The Dexcoms, the Insulet's, the Roches, the Abbotts, they're all adopting this and putting it in as fast as they possibly can. And key to all this, I want to put a plug in for that security piece. Like this IoT smart thing won't scale without that security. There's a lot of lifecycle management that has to come into the fold here. You have to be able to securely update these devices and update the models on those devices in a lot of cases. And you have to protect the data on them. Once these things are connected and you're relying on them, there's a higher threshold to integrity of the application, integrity of the data, and provability of how you made your decisions. So we need this security piece. We can't get that edge intelligence without it. But we're building it, and here it comes. So first products started hitting the market in the late 2010s. We saw Sentient launch the NDP100, which is kind of a fixed function, AI-driven chip. And so this wasn't even integrated in a processor yet. It was literally a standalone function. And that doesn't happen very often in semiconductors. Usually the entry point is integrating into an existing kind of product. But AI was coming so fast and embedded moves slower, and we didn't have time to catch up. We did launch it. Silicon Labs a few years later. We were the first wireless chip with dedicated machine learning accelerators. They're doing really well. You can see them in the back. We've got some nice demos over there. In about the 40 nanometer processes, you cannot put this stuff at 90 and above. It's just too expensive. It's arguably too expensive for 40 going forward. And we're seeing that now. Infineon just launched a very nice looking Edge family of MCUs with AI at the heart. There's no wireless on this stuff, but there's a heck a lot of kind of raw AI machine learning processing capacity. And I expect that to kind of be core to all processor portfolios going forward. So about half the products in the end market will have it and half won't. And so we're going to have products that serve both. So I was very excited to see that. So where does this all go now? We've come a long way since our first M3s, and now we're launching 22 nanometer products with more RAM than flash, or more RAM than NVM. That's kind of completely flipped the equation in terms of cost structure and software developers in these applications. We have all this wireless, we have all the security, we have all this AI. So what's going to happen next? I think that AI will become as normal embedded as the other platforms. It's already pervasive in the cloud. It's in most phones. It's coming to PCs. And I think it will be everywhere in embedded systems. There will be, again, I think half applications with and half applications without, but it'll be in every network. Your light switch may not have it, probably won't have it, but your light bulb will. We should have customers that are putting AI in light bulbs, if you can believe that. And this makes the end products fundamentally better. They can perform, they can perform their core function better. And a real-world example of this, thank you, 5 minutes. We're shipping, this is my last slide. We're shipping this stuff today. So I have a customer building circuit breakers. And that circuit breaker performs better when they're using our ML accelerator than the kind of simple threshold-based if this, then that algorithms they had in the past. So instead of kind of an expensive microcontroller honking away at 200 megahertz, just monitoring the current, they can go to a much more performant, lower power, lower cost, lower latency machine learning product. And they're shipping it now. It's in the market. So you're going to see this stuff. I also think that the edge nodes are going to become essential for model evolution. I think the companies that need to evolve the models need data that didn't exist in the training sets. And that data will only come through real-world applications where you're looking at millions of examples. And maybe 99.9% of them are just not interesting. The classifiers resolve really, really well, really, really quickly. But then that 0.1% is like gold. That's what you want to evacuate back to the servers in the cloud and do your next round of model iteration on that. And I know training data is one of the biggest things going on in this group right now. So I think you're going to need to be in the field at some point. There's going to be a self-fulfilling prophecy. You're not in the market unless you have the best models. The best models only come from those in the market. Looking forward even more, I think next generation embedded chip architectures won't be integrated the way they are today. Today, you can buy most of your stuff on one literal piece of silicon. Inside the package, there may be two, a flash and a processor. But as we go forward, the amount of compute and RAM that these applications are driving will break the chips up. And embedded may no longer have this nice one chip inside solution anymore, maybe 3, 4, or 5 chipsets to pull this together. And that may not sound like a lot to this room, but for my customers, that's a huge change. They want to put one chip on a board and be done with it. That's it. Maybe they could put 2. But they don't want to have to deal with who's my RAM vendor, who's my DRAM vendor, who's my flash vendor, who's my CPU vendor, who's my wireless vendor. It's going to get real complicated for them, and it's not going to be processing or wireless that breaks these chips apart. It's going to be AI as we go into FinFET. The third thing is operating systems and embedded have to win. They have to take over. There's more people in the world than you realize doing bare metal implementations, not in assembly, fortunately, but in C. And we have got to move operating systems pervasively through embedded. And the faster that we are able as an industry to push that, the faster the market will go. And the number of software developers who can program on an operating system far outweighs the number of software developers who can program bare metal. And the applications are getting complicated enough, you can't hold it all together in a main loop anymore. With any interrupt architecture, and it just falls apart eventually, even verifying that it's going to work in the field. And so we got to move to operating systems. I say that everywhere I can go. Please push embedded, think about operating systems. Too many of my customers are still holding back, just like they held back from the transition from assembly to C, because it got less efficient. Well, we see when, and I'm telling you, operating systems are going to win. AI can be one of the forces pushing us over the edge there. The last thing that I really hope happens is on-device training takes hold. I think you can even do that in embedded. You can do it on the phone today, and I think you'll be able to do it embedded within 5 years. So maybe final tuning of the model happens on the device. That would be great. I would like it if my doorbell cam was the only doorbell cam in the world that could find my face, or that I could train on my face the same way my phones should be the only phone in the world that can unlock based on my face. So I want on-device training to come. That will take another leap in terms of core technologies. We need good fab partners to make that one happen. So I'll end it with this. I think embedded really went from rare. MCUs went from rare to everywhere over about 30 years. Wireless is being adopted faster in that embedded space, but I think AI is going to go even faster than that. I think we're seeing the adoption rate. Once a device is connected and has a processor, it's ripe to bring in machine learning into that application for a whole bunch of different reasons. And I think there's hundreds or thousands of use cases we should talk about. In addition to core performance, like TOPS per watt or something like that, we need to get really good at talking about use cases. Because most people aren't yet familiar with just how much you can do with just a little bit of AI. So I will end it with there, as I spill my coffee.